Hi, and welcome to our talk about our work on domain generalization for semantic segmentation. In this work, we show how to utilize modern diffusion models for training segmentation models that generalize well to multiple unseen target domains. This is a joint work of me, Niemeijer, Manuel Schwonberg, and Jan-Aike Termöhlen. We are from the German Aerospace Center, CARIAD, and the Technical University of Braunschweig. Before we dive into our approach, we would like to explain what we actually mean by domain generalization. Segmentation models are trained on a certain distribution of data. This distribution of data, which has got labels, is called the source domain. We denote it here by DS. In our case, it consists of synthetic data. Generalizing from synthetic data is an especially important use case, since deep neural networks require a vast amount of labeled data for training. Such synthetic data can, for example, be created by simulation engines. If we apply this model that was trained on the synthetic distribution of DS to that same domain, so to that same synthetic domain, we get the results we can see here, which are of a quite good quality. As we can see, all relevant structures are segmented quite well. But we want to create a model that generalizes well to many so-called target domains. They are here denoted by DT 1 to 4. For us, the relevant target domains are consisting of distributions from the real-world data. Due to the large domain gap between synthetic and real-world images, the distributions of target domains and the synthetic source domain are not very similar. Hence, training a model on DS, so our synthetic source domain, that generalizes well to the real-world target domains is quite hard. We apply the model trained on DS to, for example, the target domains of Denver cityscapes or Berkeley Deep Drive. The results can be seen here in these two videos. We can see that the performance drops quite significantly when we apply the model to real-world data. This is especially true when we compare the performance that we see here to the performance that we got on the source domain, so on our synthetic data itself. Most current state-of-the-art approaches that try to solve this problem try to extend the original distributions. For example, through data augmentation like color jittering or Gaussian blurring. The problem with this is that we do not know the target domains a priori, so we do not know how to extend the distribution of DS in a structured way. Hence, most augmentations that we apply extend the distribution somewhat randomly. Our approach, on the other hand, is to create a so-called pseudo-target domain, which we denote by DPT in our case. The distributions of DPT should include all relevant real-world target domains. If we then adapt our model to this pseudo-target domain, we achieve a model that generalizes well to the relevant target domains. But how can we do that if we do not know what's relevant? Well, we do have a certain symbolic information about what is relevant to us. Modern diffusion models, on the other hand, can be utilized to generate images with regards to a symbolic description that describes the pseudo-target domain, DPT. This figure illustrates the capabilities of diffusion models. Given the synthetic GTI5 images we see on the left, the diffusion models can be utilized to create alternations that are controlled by the symbolic descriptions that we see on the top. For relevant symbolic priors, like, for example, here the country or the season or the traffic location, we can achieve quite good results. As we can see, the diffusion models alternate the content of the images quite well with regards to the symbolic descriptions. Our general approach for domain generalization then consists of two steps that can be seen here on the right side. In the first step, we generate the pseudo-target domain, and in the second step, we train a model by adapting from our source domain towards the pseudo-target domain. In order to create our pseudo-target domain, we employ diffusion models in an image-to-image way, as we saw on the slide before. That means a synthetic image goes in and is alternated with regards to a text prompt. The way we are creating the text prompts to steer the image content is of a particular importance in this case. To create diverse and relevant descriptions of the image content, we employed the following strategy. Each prompt consists of different text blocks that are concatenated. We concatenate a start block, a location block, a traffic location block, and 2 class blocks, as well as an environment condition block. Each text block can be chosen from a list of options. This way we achieve a high variety in the descriptions that we create for the text prompt. Here we can see the final examples of the prompts and the corresponding results. As you can see, the quality of the images that make up our pseudo-target domain is quite high. And the images look quite realistic. By generating the text prompts in our concatenation strategy way, we even achieve a high diversity in the images. In the first step, we have transformed the respective synthetic datasets with regards to our prompting scheme. In the second step, we are now adapting the model to our pseudo-target domain that has been created in the first step. This is done by utilizing unsupervised domain adaptation methods. The adapted model then generalizes to the relevant target domains, since the pseudo-target domain is an approximation of them. The target domains are represented by the dynamic cityscapes, the Berkeley deep drive, the mapillary vistas, and the ACDs dataset. The benchmark which we use to measure this, so the domain generalization benchmark, commonly measures the average mean intersection of union values over the DCS, the dynamic cityscapes benchmark, the dynamic cityscapes dataset, Berkeley deep drive dataset, and mapillary vistas dataset. If our source domain is the GA5 dataset, we achieve an improvement in the domain generalization benchmark of 12.3% in absolute points over our model that was trained on the source domain, so the synthetic source domain only. And we improve the current state of the art in domain generalization by 3.8 absolute points. If our source domain is Cynthia, we achieve an improvement in the domain generalization benchmark of 15.6% in absolute points over our model that was only trained on the synthetic source domain. And in this case, we even beat the current state of the art, or the previous state of the art, by 11.8 absolute percentage points. This improvement can also be seen in these videos, where the top row represents the model that was trained on the source domain only, in this case the GTI5 dataset. The bottom row represents the models that were trained on using our domain generalization approach. As we can see, we quite significantly improve the source-only model. Our approach introduces the question of the actual quality that the generated images have for the generalization task. We wondered if they are, for example, better than adapting to one of the specific target domains, for example, the dynamic cityscapes dataset. We hence subsampled the same amount of images from both datasets, so the pseudo-target domain and our dynamic cityscapes, and adapted to these subsets. We can see the resulting performances of the models on the relevant target domains, so all our domain generalization target domains we introduced, on the right side of this slide. As we can observe, the results are very similar with regards to the generalization. Adapting to the real images from DCS mostly improves the results on dynamic cityscapes itself, and does not introduce the generalization to the other target domains. We can hence deduce that the functional quality of the generated images is quite similar to that of the real-world images of the dynamic cityscapes dataset. Finally, we would like to thank you for your attention. Please scan the QR code if you would like to know further details about this work. Thank you very much.